Yes, it is our last lecture of the semester. No matter how much Amy wishes it wasn't so. But this is a springboard if you're interested in more chemistry. There's always more courses and you can take and research you can do. That's right. And you can always go back and rewatch the lectures if you want to on YouTube. All right, so please, please feel free to message with any questions you have, or just unmute yourself and speak up. So as we said, it's the last lecture of new content for the semester here. We're going to finish our discussion of chapter 23. And so there are really two main reactions that we're going to talk about today that we haven't seen yet. And the first one is reductive amination. So when we're talking about making amines, this chapter is all about amines. One way to make an amine is to start with a carbonyl compound. And the net effect here is to replace the oxygen with the nitrogen and then reduce the double bond to make an amine, right? So we talked about this part early in the semester. This is chapter 20. We saw how with just the right pH, we can get this oxygen to pick up one of these protons, and that makes this ketone or aldehyde. These R groups could also be hydrogens. It makes this ketone or aldehyde much more electrophilic at the carbonyl site, so the nitrogen can attack, push electrons up, and that gives me something like this. And then in that mechanism, we saw how there are a number of proton transfers. Right? So another molecule of ammonia would pick off a proton, alleviate that charge. Then water, or the OH group, would pick up a proton. That would make it a water-leaving group. And then nitrogen could swing these electrons and push that group out. And then it would be deprotonated again, and I would have an imine. And we saw how that entire process is reversible. If I think about the equilibrium, since water is a product of that reaction, and the ammonia I'm adding is a reactant, adding excess ammonia shifts it toward the product side, adding excess water shifts it toward the reactant side. So if we have a large excess of this, should be able to push out the water and form the imine when that reaches equilibrium as the major product. So an imine is like an amine, except it's slightly more oxidized at the carbon because there are two bonds to nitrogen instead of one bond to a hydrogen and one to a nitrogen. So the idea here is some kind of reducing agent. The simplest example we could probably think of would be a hydrogen molecule, because the nitrogen can pull these electrons away from the carbon and bond to a hydrogen here, while these electrons come in and bond here. So by breaking the pi bond and the sigma bond between the hydrogens and forming a couple new sigma bonds between the nitrogen and hydrogen and the carbon and hydrogen, that will hydrogenate and reduce the imine to an amine. And the way this looks here, it might be two separate steps. But if we could add a reducing agent in the same reaction where the imine forms, it could undergo reduction to the amine. And then if that process were much more product favored, that will also help the equilibrium that's occurring in the first step shift toward the product side as the imine is converted into an amine as it forms, it would never really reach equilibrium. The ketone or aldehyde would continue to form more of the imine as it continues to be hydrogenated or reduced into the amine. So that's the idea behind an optimal reductive amination process. We're forming an amine, so it's an amination. We're using a reducing agent, so it's a reductive amination. And we want to look for what is probably the optimal reducing agent. Some molecule that we can put in to the reaction right away, so everything's mixed together. And then as the imine forms using these reactants, that reducing agent will be there to react immediately with it. So we saw earlier in the semester and also last semester sodium borohydride used as a reducing agent. And if you recall, this was mainly used to reduce ketones and aldehydes. And that works similar to lithium aluminum hydride. It's not as strong or reactive or unstable as LAH, but the negative on the boron is not nearly as unstable as a negative on an aluminum that we would have in LAH, but still a little unstable. It's a small atom to carry such a charge imbalance. So it will deliver a hydride to a ketone or aldehyde in the same way that lithium aluminum hydride would. And usually when sodium borohydride is used, there's a methanol or a water or something to provide a proton. And so that usually converts a ketone or aldehyde into an alcohol. So we can't use this exact reagent here because in the reductive amination, we don't want hydrogens to be delivered to the carbonyl carbon when it's in the CO double bond form. We don't want our hydride delivering a hydrogen there. We want the ketone to react with the ammonia and proton to produce the imine, and then we want the hydride to be delivered. So sodium borohydride is not going to work. And so what chemists typically do is to take something that works and isn't quite right and make some modifications to it to optimize it for the specific situation we want. And so instead of using sodium borohydride like we've seen reduce carbonyl compounds, in this case we don't want to reduce the carbonyl compound. We want the carbonyl compound to be converted into an imine and then we want to reduce the imine to an amine. And that requires a more selective reducing agent, a reagent that won't deliver a hydride to a ketone, but will deliver it to an imine. And the ketone and the imine are quite similar. They have a similar amount of sterics at the site where the hydride would be delivered. There's a similar amount of partial positive here to attract the hydride in. The imine is a little bit more reactive than the ketone or aldehyde, simply because the CN double bond is not quite as stable as the CO double bond. And that may have to do with the degree to which the resonance here occurs. If I shift electrons up in the carbonyl, the resonance contributor has a negative on an oxygen, which is a little bit more stable than it would be on a nitrogen. So the resonance contribution here may be stabilizing that CO double bond a little bit more. And since it's stable, it starts a little lower in energy. Now, if we were to look at the energy diagram, the carbonyl might be starting lower in energy. The imine is a little bit higher in energy. So to make the to have a hydride attack the carbonyl, to get up to that transition state, it's going to require a fair amount of energy. For the hydride to attack the imine, since it starts higher in energy, it probably won't take as much energy to get to the transition state. So a greater percentage of the collisions will have this activation energy versus the greater activation energy. So that's why this reagent has been optimized through trial and error to be unstable enough to deliver a hydride to the imine through the lower activation energy quantity, but not so unstable that it will deliver a hydride to the carbonyl because that requires a greater amount of energy, and whatever temperature the reaction will be run at, most of the collisions wouldn't have that amount of energy. So the feature that this molecule has that's different from the sodium borohydride is the cyano group. And when we look at the cyano group, we recognize that it is an electron withdrawing group through induction. And so let's just draw that out. So if we look at that structure, there's a CN triple bond in the cyano group. And through induction and a little bit through resonance, the nitrogen is pulling electrons away, creating a fairly large partial positive there, which attracts electrons away. So what makes this reactive is the negative charge on the boron. That's why a hydride will start to pull the electrons away and deliver them to an imine. So because this carbon has some partial positive, it starts to attract electrons away from the boron, so it's not as unstable. Right? If I have a negative charge, the more electrons there are shifted toward that atom, the more unstable, the more negative there is, the more unstable it is. So by pulling some of the electrons that are shared with the boron away through induction, because the nitrogen's electronegativity is shifting electrons away from the boron, really this only becomes a large partial negative. And so it's not nearly as unstable, and it won't have the energy to react with a more stable carbonyl, but it will be high enough energy to typically react with an imine and push electrons up there. So it's the inductive effects of the CN group that makes it more selective. How does that work? It means that the boron has less negative charge on it, so it's a bit more stable. And if it's not especially unstable, it won't be as reactive. It's more selective, and so it won't react with the more stable carbonyl. It will only react with the slightly less stable imine. So this reaction can be done in one pot in a very straightforward way. It can be used to make primary, secondary, or tertiary amines. It has all the ingredients necessary. So as we said, the nitrogen nucleophile and the H plus are necessary to get it started. Right? The H plus starts off the mechanism by protonating the carbonyl, making it a much better electrophile. Then this attacks, and then as we saw in chapter 20, there are a number of proton transfer steps that occur to make the imine. Once the imine forms, it's reactive toward the sodium cyanoborohydride. So that delivers a hydride here and pushes these electrons up to the nitrogen. That may or may not happen before the nitrogen gets an extra proton though. So there's also an H plus that is present as a catalyst there. And so if the nitrogen picks up that H plus, that could happen before this hydride is delivered or after, but either way, the hydride is delivered, pushing electrons to the nitrogen. The lone pair picks up a proton, and so that's what reduces that double bond to the single bond you get here, right? So that's where this oh yeah, I lost my R group. Sorry, this should be an R group. There's an R group there. So the R group, just comes along with the nitrogen. And when the nitrogen picks up that proton, that's how I get this proton here. And the hydride is here that was delivered by the sodium cyanoborohydride reagent. So putting that all together actually works really nicely. None of the reactants are unstable enough to really react significantly with one another. And so they'll nicely and conveniently go through that entire mechanism in a pretty reliable way. So that's a really good reaction to use if you want to make an amine. It's actually the reaction used to make methamphetamine in the show Breaking Bad. So let's see if we can show how to make a compound using the reductive amination. What reactants will we need? So when I see an amine, if I want to make an amine, first thing I probably want to do is to determine whether it's primary, secondary, or tertiary. So clearly here I have 3 R groups attached there. Yeah, finally a Breaking Bad reference after all this time. If I have 3 R groups attached there, that makes it tertiary. And so that means I can really only connect 1 R group to the nitrogen at a time through the reductive amination reaction. So probably I would assume that these 2 R groups are already connected and that the ring was already there. So what I would be starting with is compounds that are going to come together and form this specific bond. So retrosynthetically, I would do a break there. And I would keep the other bonds connected. And then I have to get this carbon to connect to the nitrogen. And so the idea is I would start with a carbonyl there. And I'd start with a lone pair on the nitrogen. So in order to make this work, I would add some acid, a little bit of a strong acid catalyst, just enough to get the pH. If you recall in chapter 20, we said the pH should be roughly between 4 and 5, not too acidic, because we don't want all the sites to be protonated. We don't want the nitrogen to pick up a proton because we need this lone pair to be available to attack the carbonyl carbon. But the proton will be shuttled back and forth. Once in a while it'll end up on the oxygen. And so then the nitrogen can attack and push these electrons up. So that's just the first step in the mechanism. After that, there are some proton transfers. The oxygen turns into a water. It ends up leaving. The nitrogen shifts electrons in to make a double bond there. So that would produce this aminium ion. And we said if we use a secondary amine, typically that forms an enamine. But in this case, it probably wouldn't get that far because in addition to the acid, the secondary amine, nucleophile, we would also add the sodium cyanoborohydride. And that compound, the sodium is just a counterion, it's not doing anything. That compound would be able to deliver a hydride here to push these electrons to the nitrogen, which would form the product. So you definitely want to make sure that you're prepared to draw that entire mechanism from start to finish, and if you're not sure about steps of it, let me know. We can go over that again, or you can at least refer back to the part of chapter 20 where we talked about forming this part. The part that's new here is the sodium cyanoborohydride delivering a hydride to what was the carbonyl carbon to push electrons to the nitrogen and balance the charge. So that's your reductive amination example. And you can use that same reaction to answer the first quiz question for today. So if you have a carbonyl compound and you notice that these 5 carbons here are not undergoing any disconnect or connections, but we want to convert the carbonyl into an amine, we would just add the nitrogen and the carbons that are connected to it. as a nucleophile. Add a little bit of an acid catalyst to start that off by protonating the oxygen and making it more nucleophilic so the nitrogen can attack. And then the sodium cyanoborohydride would deliver a hydride to that carbon. Once the carbon forms a double bond with the nitrogen, it would deliver a hydride there, and electrons would swing out to the nitrogen and complete its noble gas configuration and alleviate its charge. So that's a pretty straightforward synthesis, because we can connect two large carbon groups into one structure through the nitrogen amine linkage and get a fair amount of control over, how things are connected. So just so you know, once you form a primary amine into a secondary amine, you could go further. If there was another R group you wanted to connect to that nitrogen, we could use a second reductive amination to do that. So whatever R group I want to connect to the nitrogen, I would have to have that set up as connected to a carbonyl compound with the H plus and the sodium cyanoborohydride. And after that same mechanism, you can make up to a tertiary amine this way. All right, so the nitrogen would end up connecting to the carbonyl carbon. It would initially have a double bond there. The borohydride would deliver a hydride here to make that into a single bond. So there are limitations on, what this group can look like. It's going to have to end up having at least one hydrogen on it, because that hydrogen is going to come in and actually complete the conversion of the imine to the amine. But you could have two R groups here, and they could pretty much be whatever you want. And that gives you a lot of control over the final structure. It's a very versatile way of making amines. All right, so to summarize what we talked about last Wednesday and today now, we've talked about three methods of making amines. The Gabriel synthesis and the sodium azide reaction, those can really only make primary amines. We saw those reactions, and we didn't really spend a lot of time on them or do a lot of examples, because since they can only make primary amines, they're not really as versatile and useful. And since the reaction we just talked about, the reductive amination, can make primary amines, and once that forms a secondary amine or a tertiary amine, there's a lot more flexibility in that process. So it's hard for me to imagine a situation where you would choose the Gabriel synthesis or azide synthesis over a reductive amination, because it's a reliable reaction, and you can use it if you start with ammonia to make a primary amine. If you start with a primary amine, you can make a secondary, and so on. Once you have a tertiary amine, if you want to make a quaternary ammonium ion and put a fourth R group on there, you need the alkylation reaction we talked about. So that would involve the R group connected to a really good leaving group, usually an iodide, and the nitrogen would simply do an SN2 attack and push that out, and that would install the next R group. Notice that the R group here is actually not just written as an R group, it's written as a CH2 R group. And the reason for that here especially is, in order for this SN2 to work, really what this has to be is a primary carbon that the leaving group is attached to. So that's why we have that extra primary carbon there between the nitrogen and the R group. So there are some limitations there, but there's also a lot of flexibility. So if I wanted to design this structure or synthesize this structure, and I was told I need to start with 6 carbons or less, I would probably want to start off with the nitrogen connected to the aromatic ring. So I'm not going to be able to use a reductive amination to connect the nitrogen to an aromatic ring. As we just saw, there has to be the ability for a hydride to come in here and push electrons to the nitrogen to complete that last step of the reductive amination. And so if the product doesn't have a hydrogen at this point, then that means no hydrogen came in there to complete that process. So that isn't really a bond that we're going to be able to form through reductive amination. The molecule would have to start with that bond. So in this synthesis, you'd start with the aniline as your primary amine. If you wanted to start even prior to that with an aromatic ring, you could also take the benzene ring and start by doing a nitration. So that would be HNO3 and H2SO4. And that would put a nitro group on there, an NO2. And then you'd have to reduce that with some zinc and HCl or some other metal and HCl. We saw that is how you reduce a nitro or an NO2 into an NH2. So you could also start all the way back at benzene if you wanted. But aniline is relatively cheap and it's commercially available, so there's no reason why you necessarily have to do that. You could start with the aniline. Once you have the aniline, you want to add these two groups, and you can't really add them at the same time, so we'd have to do it one by one. So maybe we first start with this ethyl group. So if I want to install an ethyl group, I would add an ethyl 2-carbon group, and I would put a CO double bond on the end of it. I would add some H plus and the sodium cyanoborohydride. So initially, just to point out, the nitrogen of the aniline would end up forming a double bond where the CO double bond was. So that's how you can kind of recognize this reaction. If it's helpful to break it down into the steps and draw the intermediate so you can predict the product, I would recommend that. So basically, if I don't add the sodium cyanoborohydride, if I just added the ketone and the H+, that would form this imine. The nitrogen would keep any R groups it had connected to it, and then it would replace the oxygen and form a double bond to the ethyl group if I have an ethyl group. And so then the hydride from the sodium cyanoborohydride would come in here and push these electrons to the nitrogen, and then it would pick up a proton. So that would hydrogenate in effect or reduce the double bond there to a single bond. So that would give this structure here. And that puts the ethyl group on the nitrogen. And now I need to put this group on the nitrogen. So the last step there would involve setting that group up as a carbonyl compound. Right? Whichever carbon I want the nitrogen to connect to, that carbon would have started as a CO double bond. Add the other reagents, and that reaction should go. Right? So again, the oxygen gets protonated, the nitrogen attacks the carbonyl carbon. That's how the nitrogen and the carbonyl carbon connect. That pushes electrons up to the oxygen right when the nitrogen attacks there. Then the oxygen is made into a leaving group, it leaves, the nitrogen forms a double bond with the carbon, and then the hydride breaks that double bond into a single bond, and you get the product. Any questions about that? This is a reaction we talked about in chapter 21. We were talking about carboxylic acid derivatives. We said an amide is a carboxylic acid derivative. And we said the main way to make that is to start with an acid chloride or an acid anhydride. because those both have great leaving groups. The nitrogen can attack, push electrons up. When they swing back down, it'll push out that leaving group. Same thing can happen here. Electrons would swing up, and when they'd swing back down, it would push out this carboxylate leaving group, which isn't quite as good as the chloride leaving group, but they're both relatively good leaving groups. And once they leave, they're not really coming back in due to their stability. In the case of the anhydride, when the carboxylate leaving group leaves, it can pick off one of these protons, because once the nitrogen attacks, it's going to become positively charged. It has to have a proton, at least one, so that that can be picked off and the electrons can remain here instead of being shared as a lone pair, right? So if I had another hydrogen here, it'd be positive, it'd be unstable. This lone pair is really not going to be accessible to share with a proton because it's engaged in resonance, a significant resonance contribution there. So it's a pretty straightforward reaction. If you recall a couple details about it, typically if you use the acid chloride, you'd use 2 moles of the amine. Because the Cl- leaving group is such a terrible base, it'd be the second mole of the amine that would pick off the proton from the first one and generate that lone pair there instead of having a positive charge on the nitrogen. If you use an anhydride, you don't need that because the carboxylate leaving group of the anhydride can pick off that proton, as we said. And so that's to remove a proton from the compound that's nearly the product, which would have a positive charge, right? So we need another base, usually an extra mole of the amine or the carboxylate leaving group, to pick off that proton and give the product. Polysubstitution we don't have to worry about. So what does that mean? Well, when we were talking about amines, we said, if you have like a primary amine and you add some kind of primary alkyl halide, the amine can pick that up and go from a primary amine to an ammonium ion, and then another unit of the nitrogen can pick off one of those protons, and you can get from a primary to secondary amine. And you could do that reaction again and go to a tertiary amine. That's what we mean by polysubstitution. If we wanted to just put one R group on, once we do that, if there's still any unreacted alkyl halide, then we can't really prevent the nitrogen's lone pair from picking that up again. So that's why we're not worried about that happening in this reaction, because once the nitrogen of the amine attacks and pushes out the leaving group and then is deprotonated to form an amide, the lone pair now is engaged in resonance. So the lone pair is not really nucleophilic anymore. An amine is nucleophilic, there's a nice partial negative there, and the nitrogen's lone pair is ready to be shared with a carbon. An amide is not really nucleophilic in any significant amount because the lone pair is already involved in resonance. It's not really available to be shared effectively with another carbon group, so we don't really see that attacking anything for the most part. So that's a nice advantage of this reaction. If we want to form an amide with a couple hydrogens here, or even just one hydrogen, we don't have to worry about that being replaced by another CO double bond group, and we don't have to worry about the nitrogen coming in here and attacking and connecting another CO double bond to it. You can use this acetyl group as a protecting group, which we'll see how to do in an example on the next slide, although there are some limitations with that we'll see as well. So let's say you want to do this reaction here. This is an issue. because if we add Br2, if you remember from chapter 19, the nitrogen's lone pair is engaged in resonance here, and it makes the ortho and para and other ortho positions quite nucleophilic because of the minor resonance but significant resonance contributors where the lone pair pushes these electrons onto the ortho and para carbons. Those carbons are pretty nucleophilic, so they can attack a Br2 and kick out a bromine, and then upon rearomatization, you would end up with a bromine at every one of those ortho and para positions. So that's a problem. So if you wanted to do this reaction, it won't work. An alternative, though, would be to convert the amine into an amide by adding this acyl chloride. Then the amide's lone pair is still involved in resonance, so it's still activating the ortho and para positions, but now there's more sterics blocking the ortho position somewhat, and the lone pair is also engaged in resonance up here, and so the degree to which it contributes to negative charges on the ortho and para carbons is less, and with less partial negative there, it won't be as likely to attack. So then when I add the bromine, I can get almost exclusive para substitution due to the sterics and lower reactivity of the lone pair. But then I have a problem, because if my goal is truly to make this compound, and I've been able to utilize the amide group to make sure that I only get bromine to connect on the para position where I want it, then I still have to remove the protecting group. And as we saw in chapter 21, cleaving an amide and getting the amine is a reaction that requires some pretty harsh conditions. It requires a lot of heat and time, and usually concentrated acid. The base doesn't really work quite as well. But you can use either of those conditions depending on the structure. You might get the reaction to work. So this is another example of using a protecting group to aid in the production of a product that would otherwise not be readily formed. Another example of that, if I wanted to do a Friedel-Crafts reaction on aniline, that wouldn't work very well. Right? Normally in the Friedel-Crafts reaction, let's say we're doing a Friedel-Crafts alkylation. In a Friedel-Crafts alkylation, let's just keep it simple. Let's say we wanted to add a methyl group to the ring. Well, we would put a leaving group there, and the aluminum would be attracted to that, or the lone pair of the chloride would be attracted to the aluminum, and that makes the chloride a much better leaving group. Now that the chlorine is positive, it's really attracting these electrons, so that makes the methyl group even more easy to attack. So when the electrons swing in here, they could come out and connect to that methyl group from the ortho position, or they could swing in here and attack it from the para position. So one issue with that is we're going to get some ortho-para competition. It's going to give it a mixture of products because the NH2 isn't really sterically hindering enough to block the ortho position and preferentially give the para substitution. But the other issue, which shown here on the slide, is the lone pair of the nitrogen would also be attracted to the Lewis acid catalyst, not just the chloride, which is what we want. And so the attraction of the nitrogen to the Lewis acid catalyst would form this intermediate, and then with a positive charge, that would start pulling electrons out of the ring, and that would give some significant partial positive in the ring and make it much more difficult for that to use its electrons to attack a methyl group, because that's only going to make it more positive. Right? So when we looked at EAS reactions, we said EAS reactions work best when the ring has more negative charge, because that negative charge has to come out and attack something that has a lot of positive leaving group. If the ring's positive, it's not going to be attracted to or attack something that's also positive. So this screws up the whole EAS reaction, having the nitrogen attract to the Lewis acid aluminum chloride catalyst. So we would do another protecting group to get around that issue. So again, having the nitrogen attack here, push the electrons up. When they swing back down, it'll push out the chloride. Another molecule of this would deprotonated, so I would only have one proton, making the structure neutral. So that's the formation of the amide, and that's acting as a protecting group. It's a little bit bulky, so it's blocking the ortho and para positions. And now the lone pair is engaged in more resonance, so it's not nearly as likely to start attracting to the aluminum, which was the problem we had over here. So that's another advantage. So adding the protecting group creates sterics to block the ortho-para position. It kind of occupies the lone pair in resonance, so it won't come in and attract to the Lewis acid catalyst, and then that allows the Lewis acid catalyst to get involved with the methyl chloride to make that a much better leaving group, which means that the ring will be able to attack it and do the EAS reaction, the Friedel-Crafts alkylation. But then again, we have to remove this. If we wanted to make the amine product, we put the protecting group on so that it facilitates a more effective and efficient EAS reaction, but then we have to remove the protecting group. So a lot of times a protecting group is a nice strategy, but it's always going to add at least 2 additional steps to your synthesis, putting the protecting group on and taking the protecting group off. And if the conditions required for that are especially harsh, then it might start causing side reactions you don't want. And if your percent yield for those 2 additional steps aren't very high, you might not get a very good yield overall. So protecting groups can be nice, but they're always going to cost you a couple extra synthetic steps, and if they don't have high yields, then an alternative approach might be recommended. So then the last quiz question of the semester was this one here. And so the idea is, how do we convert benzene into this amide group? And so the idea here is to first install the nitrogen on the ring. So you'd start with nitric acid and sulfuric acid. Those 2 combine, if you recall, to make a nitronium ion, which is a great electrophile. The ring would attack that. And then upon rearomatization, the ring would give a nitro group at that position. So we've got the nitrogen now attached. And the second step would be to reduce that nitro group to the amine. So you could use zinc and HCl, or a couple other metal catalysts with a proton source will do that. If you recall, the metal has loosely held electrons. It will donate to the nitrogen to push electrons up to these oxygens. The proton will protonate the oxygens and make them water leaving groups. And then when the electrons come into the nitrogen and push those water leaving groups out, the protons will be able to be picked up by those lone pairs, and that's how we would get protons connected to that nitrogen. So the next intermediate that would result after that step would involve converting the nitro group into an amine. Once I have the amine, now I just need to make this amide. So to make the amide, I would keep the same carbonyl compound with the same R group here, but I would just make this an acid chloride. So if I can make this acid chloride or buy it, the nitrogen should attack there, push electrons up, they'd swing back down, push out the chloride, and then it would just have to be deprotonated since it has 2 protons here and only 1 in the product to make it stable and balanced in charge and free up that lone pair to be engaged in resonance with both the ring and the carbonyl. You'd want to use 2 moles of the amine so that one could attack, push out the chlorine, and then the other could remove the proton as necessary from the one that attacked to produce the product. And that would work well for that. So this is another reaction the textbook spends a fair amount of time on. I'm not going to actually cover this. I really almost never ask questions about it. It's kind of a little bit of overkill, I think, on the idea of doing an elimination. It's very rare that you would have an amine that you would want to eliminate. I mean, this elimination eventually produces an alkene. And so the idea here is you're starting with an amine group and you're picking off a proton. You're basically making the amine into a decent leaving group and then using a base to pick off a proton. And this is not anything I've ever really seen done in the literature or by anyone I know who's done these reactions. Not to say it's not necessarily useful in certain situations, but we've learned lots of different methods to make leaving groups and take advantage of using a base to pick off a proton in a regioselective way to push out a leaving group and control the position of a double bond in an alkene that we might want to make. So I'm not going to add more detail to that in the context of this reaction. So just be aware that this reaction exists if you ever needed to use it in the future, but I'm not going to ask you about it. So you can rely on the other reactions we've already discussed. If you need to do an elimination reaction, I won't expect you to convert an amine into a leaving group and then have it eliminated. So the other reaction that we definitely want to cover today, though, is this reaction where an amine group gets converted into nitronium. Not a nitronium. Why is the word not coming to my mind right now? Diazonium salt. So converting an amine to a diazonium salt is actually really useful, and we're going to see that this reaction provides a lot of variety for synthetic purposes. So the first thing that is involved in this reaction is a reaction between sodium nitrite, which is NO2 minus, and HCl. So in some textbooks, they show the NaNO2 and the HCl as your reactants. Well, when these reactants come together, the oxygen picks up a proton and I get nitrous acid. So instead of showing these two, sometimes you just see nitrous acid. Sometimes it's written as HNO2, sometimes it's written as HNO. Either way, you've got 2 oxygens, a nitrogen and a hydrogen. This, I always kind of gravitated toward this as an undergraduate because it kind of sounds like, oh no, this reaction is out of control, oh no. Maybe that will help you remember it. But if you're using HONO or nitrous acid in the presence of HCl, it can pick up another proton and that can act as a leaving group. And then I get this nitrosonium ion, which don't worry about the naming of that specifically, but this ion is a great electrophile. Right? So obviously this is the major resonance contributor because both elements have complete noble gas configurations, but this minor one also exists. So the positive exists over both the oxygen and the nitrogen itself is a really great electrophilic site. And so we can imagine a nucleophile like an amine attacking this nitrogen to complete its noble gas configuration and alleviate its charge, or attacking this nitrogen so electrons can swing out to the oxygen and alleviate its formal charge. So that's kind of giving you a little intro into what we're going to see happening with this nitrosonium ion. Very electrophilic, very easily attacked by even a weak nucleophile, and an amine is a pretty decent nucleophile. So if I have a primary or secondary amine, either of those, primary would have 2 hydrogens, a secondary would have an R group there. Either of those can attack the nitrosonium ion, and so that's what we're seeing here. Once that attacks, the best base that might be around will be water. It might be another molecule. The amine could come in here, but one of those substances would come in and pick off a proton to balance the charge on that structure. And we don't see a lot of bonds between highly electronegative atoms, especially between oxygen and oxygen, but nitrogen-nitrogen bond isn't too unstable. After that attack occurs and the proton is picked off, and we get this structure here, this hydrogen here could also be an R group, so just to clarify that, depending on whether we used a primary or a secondary amine to begin with. What's going to happen next in the mechanism is this oxygen is going to pick up a proton, and then this oxygen is going to pick up this proton. And okay, so this would be specifically if we have a primary amine. So this wouldn't be an R group. I got a little distracted by the secondary amine reaction there. So if you have a primary amine specifically, and there are 2 protons to begin with, after the attack on the nitrosonium ion, a water will pick off 1 proton to neutralize that charge. The other proton can still be picked off. So if this oxygen gets protonated, and these, you got to remember, these proton transfer steps are very fast and they're very reversible. So they're constantly happening in both directions. So it's not like this oxygen will necessarily be the next thing to pick up a proton. Maybe the nitrogen will. But then maybe it'll bump back off. So once in a while, we still have acid around. The oxygen would pick up a proton. And then if water picks off this proton, electrons swing in there. I could form a double bond between those nitrogens, and electrons would swing out to the oxygen. And so that would give me this. All right, so we just formed a double bond between the nitrogens. We've got an OH group now. And so if that picks up another proton to make a water-leaving group, another lone pair can swing in and push that out. And this is what I get. This is a diazonium salt. So the purpose of this is to convert my primary amine into a diazonium salt. And so I'm going to use HONO and some H plus to do that. And that's the mechanism. We just talked about the mechanism through which that will produce this diazonium salt. And what's nice about a diazonium salt is this is a really good leaving group. It is such a good leaving group, it can leave from almost any carbon. So far throughout OChem 1 and 2, we've said, well, we would never expect a leaving group to leave a methyl or even a primary carbon because the carbocation would be especially unstable. And we said we would never expect a leaving group to leave an aromatic ring because if it left, the resulting empty sp2 orbital that's relatively compact would be especially unstable. Well, this leaving group is really good at leaving, and because when it leaves, it produces nitrogen gas, which will then bubble out and not be able to really come back in, the carbocation that would result, even though it's really very unstable, it wouldn't take long for a few of these to leave to produce a significant amount of that. And so that means now we have the ability to bring in almost any nucleophile. We'll just write X, because that's what they have here in the slide. Any nucleophile should be able to then come in and replace that. So in essence, the overall impact of this reaction is to convert an NH2 on really any R group, even a ring where we normally can't form a carbocation, make it into a super leaving group, and then replace it with pretty much anything we want. So I'm probably not going to ask you to draw the mechanism where the amine converts into the diazonium salt. But I might ask you some details about this reaction. And so the idea here is, what you want to know is that these conditions will go through the mechanism we saw. You don't have to necessarily know every detail of that mechanism, but that will convert your primary amine, no matter what R group it's attached to, pretty much into a nitrogen leaving group, an N2 leaving group, which is not just really stable after it leaves, but it also has a formal positive here to really physically attract these electrons. So even though it might take a significant collision to pull those electrons away from the carbon and leave this empty sp2 orbital, if there is enough energy to do that, once the nitrogen leaves, it really has a hard time coming back in because it's so stable as an N2 molecule with the triple bond and no formal charge. And as a gas, it will start bubbling out of the reaction. And that will create a situation where any nucleophile can pretty much come in and replace that. And so we see, I'm not sure why, but copper as a spectator ion seems to be effective in bringing in a counter ion as a nucleophile. So a bromide, a chloride, an iodide, a cyano group, those all can come in and replace that excellent leaving group and get connected to that carbon where the leaving group left. So now we have another way of adding a halide to the ring, or a cyanonucleophile if we want to add that to the ring. And there are then reactions that can undergo, if depending on what functional group we want to be connected to the ring in the end. So here's an example illustrating that particular synthesis. Right, so these will be the steps to install that group here. Right, so we already have an isopropyl group here. This is an ortho-para director. And we saw in chapter 19 how its induction, where it shifts electron density in, makes it more likely that an EAS reaction will happen ortho or para to it. But since this is a bit sterically hindered, it's probably going to block out the ortho positions somewhat until the para position is going to be preferred. So the nitronium ion would be produced by these. The ring would attack that. And so initially I would get an NO2 there. After that step, the iron, we usually would see zinc or iron used with an H plus to convert the NO2 into an NH2. And then the HONO NHCl or sodium nitrate NHCl would convert that into this super good leaving group. And then if I add a cyanonucleophile, that would be replaced initially with a CN. And then if you recall, one of the reactions the cyano group can undergo is a hydrolysis with H3O plus water and heat. And that would convert the cyano group into a carboxylic acid. So it's a few steps there, but a lot of times these steps occur in sequence, specifically because you can put a nitro group on the ring wherever there was just a hydrogen. The nitro group can be reduced to the amine. The amine can be converted into the diazonium salt, and then that can be replaced with almost any nucleophile, including a fluoride ion. So now we have a way of putting a fluoride on a ring. So if you ever see a fluoride coming into the structure, you can be pretty confident that it went through this diazonium salt, and this delivers a fluoride ion pretty readily to act as a nucleophile and to replace that leaving group. You can use water. It's a weak nucleophile, but this is a great leaving group, so it can come in there and then it would be deprotonated by another water. You'd end up with an OH. The H3PO2, I'm not really sure exactly how this one works. It must be producing some kind of hydride to come in as a nucleophile to replace the leaving group. But that also works. I mean, typically that's not a reaction you usually want to do because, usually you can get an aromatic ring that's got hydrogens all over the place. So usually the goal is to replace the amine group with some other nucleophile, but that's also just illustrating more options there. And then one other thing that you can do with this diazonium salt is attack it with another structure. Right? So what we were saying a minute ago is, since the diazonium salt is such a good leaving group, usually our goal here would be to get it to leave from the ring, become nitrogen gas, and then have some other nucleophile come in and replace it. But if we look at the diazonium salt, it's not just this nitrogen is positive. It's not just pulling these electrons toward itself. It's also pulling the shared electrons toward itself, which means this nitrogen, right? Normally we think of two nitrogens having the same electronegativity, but if one has a formal positive, that positive is going to attract electrons better. So these electrons already kind of pulled away, creating a partial positive here through induction. And that can attract electrons. So we can imagine a nucleophile in general also attacking here and pushing electrons to the other nitrogen. And so in this particular case, we're designing a synthesis for a dye. This is this particular structure is a dye because of its long-range conjugation. Right? This lone pair is in a p orbital, one of those lone pairs, not both of them. Then that overlaps with the p orbitals all the way around the ring, which overlaps with the p orbitals on the nitrogen, which overlaps with the p orbitals on the neighboring ring. And all that p orbital overlap creates a whole bunch of molecular orbitals, right? There's 6, 7, 8, 9, and 6 more. 15 total p orbitals overlapping, so that means there's going to be 15 molecular orbitals. And with 15 molecular orbitals, the energy gap between the LUMO and the HOMO is going to be quite small. It's going to be just in the visible part of the spectrum that light has the energy necessary to excite an electron from the HOMO up to the LUMO. And so when that wavelength of visible light is absorbed, you don't see it with your eyes, you see the other wavelengths, and that gives you the color. Right? So these types of compounds are dyes. They're very common dyes. And depending on the specific functional groups that you might put here and here or at other positions on the ring, those functional groups will have a small impact on the energy gap between the HOMO and the LUMO, and they will affect the color of the dye, because if I change that energy gap a little bit, then it will be a slightly different wavelength of light that's absorbed, and that will produce a slightly different color. So you want to be aware of these types of compounds, and how they're made is typically through making a diazonium salt and then having a ring that's relatively nucleophilic, because these lone pairs can shift in, and that creates a nice partial negative here. So the electrons from this carbon will reach out and collide there and stabilize the charge on the nitrogen. And then there's a little section here about rings or cyclic compounds that have nitrogen, right? So if you recall, the term heteroatom refers usually to nitrogen and oxygen. Really, it's anything that's not hydrogen or carbon. So a heterocycle is a ring that includes something other than just carbon. So maybe a nitrogen or an oxygen. So nitrogen heterocycles, specifically rings that contain nitrogen. And these are actually really common in not just in organic chemistry, but in biology a lot, and also as well in pharmaceuticals. So you can see, getting from a sophomore level organic chemistry year, which you all have been through now since you're in OChem 2, to the point where you could design synthesis for these types of really complicated structures is still a long way to go, right? So if you were interested at all in synthesis and you wanted to design and synthesize new drugs, could make a big difference in people's lives. This is just to illustrate how complicated those structures are. A lot of them contain a lot of the different functional groups we've seen. There's drugs that contain pretty much every functional group, including lots of drugs that have amines. And when the nitrogen of an amine is incorporated in a ring, that's called a heterocycle. So we want to look at a couple simple heterocycles and some of the reactions that they can do. If you recall, pyrrole, which is this structure here, is aromatic. It meets all the criteria to be aromatic. It's especially stable. It's got 1, 2, 3 pairs of an odd number, 3 pairs of pi electrons in a fully conjugated continuous ring. And so that ring can undergo aromatic, electrophilic, aromatic substitution reactions like other aromatic compounds like benzene can undergo. So it's just one example of that. It would form something very similar to the sigma complex that we saw in EAS reactions. And then upon re-aromatization, some kind of base would have to pick up this proton and re-aromatize the ring. And so you can substitute hydrogens on that ring for different groups through an EAS reaction. So you're going to be aware of that. Imidazole is another heterocycle. It's very similar to the pyrrole we just saw, but it's got an extra nitrogen. So these two nitrogens are very different in the structure, not just because one has a proton and the other doesn't, but this nitrogen's lone pair is in an sp2 orbital. This nitrogen's lone pair is in a p orbital. And that is necessary for it to overlap with the other p orbitals for these other pi bonds and make the ring aromatic. So imidazole has one nitrogen with a lone pair, and that lone pair is engaged in the resonance, keeping the ring aromatic. The other lone pair is in an sp2 orbital. It's much more available to maybe act as a base and pick up a proton, but the ring has the two nitrogens with significantly different environments. And this is the basis for histamine. So histamine is a compound that a lot of people have allergies to, which is why you would take an antihistamine if you have certain allergies, especially this time of year. Also, there are receptors in your tissues that detect the structure and cause an immune response to it if you're unlucky enough to experience certain types of allergies. So it's the partial charges here and the shape of the structure that would engage with some receptor site in some protein to cause that response. We've talked about pyridine a fair amount. We know pyridine can act as a weak base. It can pick up a proton. If it does, you would get a pyridinium ion. And we can look at its pKa. It's kind of in the middle. So it's a weak acid. And so it can shift back and pick up the proton. So this is an equilibrium that can readily form here. When pyridine picks up a proton, it's still an aromatic ring. So it stabilizes the proton pretty well. It doesn't stabilize it as well as it would if the nitrogen's lone pair were in an sp3 orbital. Right, so over here, this is just for comparison. We talked about other amines like cyclohexylamine. Make that aromatic. Cyclohexylamine. Its lone pair is in an sp3 orbital, so it's more elongated. It's not held as close to the nucleus. It's easier for that to overlap with a 1s of a hydrogen and pick up that proton and be stabilized. So it's a weaker acid. Once it picks up the proton, it holds onto it better. But pyridine is okay at holding onto that proton as well, even though its orbital is a little bit more compact and the electrons are held a little closer to the nitrogen than the proton. If you recall, pyrrole has a much lower pKa once it's protonated, because if it gets protonated, the lone pair is no longer present that it needs to make that ring aromatic. So the ring wouldn't be aromatic once it's protonated, but if it loses the proton and puts the lone pair back there, then it would be aromatic. So in its protonated form, it's actually a strong acid. And we'll pretty much give that proton up to water every time to make this ring aromatic, because it needs the lone pair in a p orbital to overlap with the other p orbitals to keep the aromaticity of the ring. So there's also an analog to pyridine called pyrimidine, and this type of structure is present in a lot of the, well, I think in a couple of the DNA base pairs that are in your DNA, and that contributes to the properties and structure of DNA. I don't want to go into too much detail about that, but just to point out, those structures do readily exist. So, there's a lot more out there than what we really have time to get into detail on. And so we like to finish up each new functional group discussion with a little bit of reminders and details on some of their spectroscopic intricacies. So if you recall, when it comes to IR, there are some specific signals we normally look for that indicate an amine, and that depends on whether it's a primary, secondary, or tertiary amine. Right, so a primary amine has two NH bonds, and we said there's two ways those can stretch, either at the same time, symmetrically, extending and contracting at the same time, or asymmetrically, where one gets longer as the other gets shorter, and then vice versa. So since there are two ways that can vibrate, there are going to be two signals for the NH stretch in the IR. And those two signals would come usually between 33 and 3400. And they're not going to be as strong as an OH stretch, right? So how do we tell the difference between an OH stretch and an NH stretch? Well, one thing is, if it's a primary amine, the signal will have two little peaks there. If it's a secondary amine, it'll usually just be one. Because if it's a secondary amine, there's only one proton connected there. So it's basically just stretching with one frequency, and it gives one peak. If it's a tertiary amine, there's not going to be any signal around 3400 or 3300, where we normally expect that to be. If it's an alcohol and it has an OH stretch, that usually gives a much bigger broad signal because of the polarity of the OH bond being more polar than the NH bond. Right? So you're looking for a difference in the strength of the signal, as well as, if you suspect a primary amine, the number of signals relating to the number of ways it can vibrate. Should be aware that if you add an acid, that can change all of this, because adding an extra proton can change the ways that these things stretch. And for a tertiary amine, which normally wouldn't have a proton on the nitrogen, protonating that lone pair will cause a stretch. So if I have a tertiary amine and I take an IR and don't see a signal for the NH stretch, but then I treat my substance with acid, protonate it to create an NH bond, then I would see a signal for the NH stretch. So that's a really nice way of confirming the presence of a tertiary amine. So don't forget about the NH stretch signal in the IR for amines. In terms of the proton NMR, there's two things we want to concern ourselves with. One is, what is the signal going to look like for any proton that's directly connected to a nitrogen in my amine structure? And the second thing is, how is the nitrogen going to affect protons that are on neighboring carbons? Any proton that's further away than that isn't really going to be affected by the nitrogen, so we're not really worried about that. So one thing about protons that are and their signals, when they're directly attached to a nitrogen, they're exchangeable. They're generally going to be exchanged with a solvent or trace amounts of acid or base, and the rate of proton transfer is very fast. It happens in a very fast time scale, faster than the NMR machine can get the data. So if this NH proton is coming off and being replaced with a different proton, and that's coming off and being replaced with a different proton, the signal doesn't get produced for the hydrogen in a very consistent way. Right? So, in other words, if the hydrogen were always attached to the nitrogen, then its environment would always be exactly the same, and every hydrogen would give the exact same signal, and they would all appear in the same spot. It'd be a very sharp signal. But that's not really the case, because for any given moment in time, there's going to be protons that are gone, they're coming back in. Since they're being constantly exchanged, what we see in the NMR is really an average signal for all those protons. Some of the ones that are nice and strongly attached will give a certain signal. If the bond starts to stretch as it starts to break, we'll give another signal. So really I'll have all these signals right next to one another, and all these sharp signals right next to one another, they actually end up producing a broad signal. So when you see an NH proton, it's hard to say for sure what it is, because it could really appear in a pretty broad range of the proton NMR scale, depending on what the solvent is, how concentrated it is, what the temperature is. But usually we see broad signals that don't engage in splitting because the protons are constantly being exchanged at a rate that's faster than the NMR experiment takes place. And since they're exchangeable, that means if the solvent has exchangeable deuteriums, the proton may be replaced with the deuterium, which means the signal may completely disappear altogether. Right? So there's a lot of variability in what you might see in a proton NMR for the proton signal if the proton's directly connected to a nitrogen. And this all also applies to protons directly connected to oxygens. When we talked about that, we said the OH and now also the NH proton may give a signal somewhere on the scale. We don't know exactly where. It will probably be broad with no splitting, but it may also disappear completely if that proton has been replaced with the deuterium. So there's a lot of possibilities depending on exactly how you run that NMR. For protons that are on a carbon, they're not exchangeable, right? So these electrons aren't going to be stable as a lone pair on a carbon. So it's not like this proton's given away and then a new one comes in. This proton is stuck here. It's not going anywhere. So whatever its environment is, every molecule that has a proton on this carbon is going to have the exact same environment. They're all going to give the same exact signal, and the shift for that signal is going to depend on that environment. And so if the nitrogen is here directly connected to the same carbon de-shielding, that's going to cause a significant de-shielding of that proton. Not nearly as much as oxygen. So let's just compare. So let's say we have 3 carbons and an oxygen. And we're looking at the proton on the same carbon that the oxygen is connected to. With a highly electronegative oxygen, which is significantly more electronegative than a nitrogen, 3.5 for its electronegativity versus 3.0. The more electronegative atom withdraws and deshields the carbon and thus the hydrogen a lot more. And so typically this hydrogen is going to be deshielded by about 2 to 3 ppm from where it would normally be. And normally a CH2 comes around 1.2. So that's going to put me, probably between 3 to 4 ppm. Actually, this is going to be more like 2.5 to 3, I think. With the nitrogen not being as electronegative, and so the deshielding isn't as severe, the downfield shift isn't as severe. So that's why we usually see this usually between 2 and 3 ppm. And the shift in the carbon NMR also isn't as severe. And if for the carbon is directly connected to an oxygen, that signal is usually between 50 and 100 for that carbon. When you've got a nitrogen, it might be right around 50 or even a little bit below that. So you want to be aware if I give you a problem involving carbon or proton NMR, you're looking for signals to be deshielded if there's a nitrogen right nearby, but not as much as you would expect if there were an oxygen. And in terms of the mass spec, because a nitrogen can have up to, well, it will typically have 3 bonds. If we had an oxygen here, it would only have 2 bonds typically to be neutral in charge. The nitrogen brings in an extra proton, right? So the oxygen's mass is about 16, nitrogen's mass is about 14 for the most common isotopes at least. But when we add an extra proton, that adds an extra mass unit, and so that's why we get an odd mass usually. So if there are an odd number of nitrogens, typically there's an odd mass. And there aren't many other features on a structure that can create an odd mass for the molecular ion in the mass spec. So just to remind you how the molecular ion forms and what it is, if I have some molecule and I put it in to a mass spec instrument, the mass spec is going to knock some electron out. The mass spec is going to hit that with energy. It's going to overcome the attraction of one of those electrons and knock the electron out. If the electron gets knocked out, then you get a charge. The molecule might fragment, but if it doesn't fragment right away, the detector will detect the full structure, minus the electron that gets knocked out. So that's the molecular ion. The molecular ion is the original structure missing an electron, so it has a positive charge. It has to be positively charged for it to attract to the magnet and be detected in the instrument. But since all it did was lose a single electron, its mass is still the same. So the molecular ion has the same mass as the original structure with the most common isotopes. And so when an odd number of nitrogens is connected with the number of hydrogens those usually have, that usually ends up giving you an odd mass for the structure, which means you'll have an odd mass for the molecular ion when it loses a single electron, becomes charged, and gets detected by the instrument. So you want to keep that in mind as well if I give you some data and you're trying to determine the structure, or if I give you a structure and ask you about the molecular ion for the molecular ion mass for that structure. All right, that is it. Obviously, this shouldn't say exam 4. This should say exam 13 now. Lots of good practice. And just to remind you, next week on both Monday and Wednesday at the normal time, 1 p.m., join me on Discord, and we will have a review session where you have the opportunity to earn bonus points. Right, so I'll have you communicate in your individual group chats to come up with your lab group's answer to the questions that are on the PowerPoint slide for the final review. final exam review, and then you earn bonus points for getting those correct as a group. Just like last semester, there's also some extra synthesis practice here for those of you who want to check that out to prepare for the final. And then, you know, anytime you're running up against any issues with these practice problems or any others, please let me know.